Now that we know about logarithmic functions and we understand the laws of logarithms, we're finally ready to apply logarithms to solving exponential equations. So we've looked at exponential equations already, and of course an exponential equation like the one below, 2 to the power of x equals 50, is exponential because the unknown value that we're looking for is in the exponent place, 2 to the power of x. Now, unlike before, we're not able to write 2 to the power of x and 50 as a power of the same base. So this is clearly not one of the examples you would have been given a couple days ago where you asked to solve, okay? Without logarithms, we can only kind of guess and check at what the answers might be. So if you think about what x might be, it's got to be between 5 and 6. 2 to the power of 5 is 32, and 2 to the power of 6 is 64. So it's somewhere between those values, not halfway or anything like that, because it's not linear, but somewhere there. Okay, so there's a very simple way to do this. If 2 to the power of x is equal to 50, then it must be that the log of 2x, 2 to the power of x, pardon me, is equal to the log of 50. And that's just I mean, a lot of people say, are you just taking the log of both sides of the equation? Yeah, that's absolutely what I'm doing. I'm taking the log of both sides of the equation. And I'm able to do that because if I know 2 to the power of x is equal to 50, then their logs had better be equal as well. I mean, log is a function, okay? When you take the log of something, you're only going to get one answer. So if the something that you're taking the log of is the same, then the log of the somethings will be the same. From there, we can actually just use our power rule, which means that log base 2 to the power of x is really the same as just x log 2. Once I've completed this step, that's a very important step because now this is no longer an exponential equation. It's actually technically just a very simple linear equation. You need to remember that log 2 and log 50 are really just numbers. Okay, so if I divide both sides of the equation by log 2, I'll get an exact answer of log 50 divided by log 2. Now notice I haven't said anything about the base yet. I've chosen not to write a base, which means I'm probably talking about base 10, though to be honest, I could do this in any base. I'm going to do it in base 10 though, because I have a base 10 button on my calculator. And I can now use my calculator if I want an approximate value for x. I just do the log of 50 and I divide that by whatever the log of 2 is. So and you get, sure enough, it's about 5.64. Okay, so those are the kinds of equations we're going to work on today. Now, this is a very simple equation. You just have a power equal to some other number, take the log of both sides, use the power rule, divide by, in this case, log 2, and you've got your answer. So as the equations get more complicated, the goal kind of remains the same of trying to reduce all of the other equations so they look more like example number 1. Sometimes in math, we call that reducing to a known problem. We take some equations that are complicated and we try to make them look like this equation. So that's very true about question number 2. Okay, it's an exponential equation because the x is in the exponent place. If I want to make this equation look more like the first example, then I might start by, I mean, I put the brackets around the 5, but it doesn't matter instead of the 3. I might start by adding 9 to both sides. And then, okay, and notice the 3 there. I can divide both sides by 3. And since 9 divides by 3 nicely, I just get 3. And now it looks a lot like our first example. We're ready to take the log of both sides here. Okay, now we've taken the log of both sides. We can now use the power rule to bring the exponent down. Now when I do that, I've got my exponent 2x minus 4. I'm going to multiply that by log 5. I do need brackets somewhere. I would normally just throw them in there, like so. And now again, it's log 5 and log 3 are just numbers, okay? So 2x minus 4 times log 5 equaling log 3 is really just a linear equation again. I'm going to divide both sides by log 5. I get 2x minus 4 equals log 3 divided by log 5. Again, that's just some number. I'll worry about that later. I can add 4 to both sides. and get log 3 divided by log 5 plus 4. And then finally, to solve for x, I'll divide by 2. Now, when I divide log 3 over log 5 by 2, dividing by 2, you can imagine it's the same as timesing by a half, or you just put a 2 in the denominator, and then divide 4 by 2 as well to get 2. That's my exact answer. Log 3 divided by 2 times log 5 plus 2. That's a perfectly good exact answer. You could notice that's the same as this right here. The log of 25, just using the power rule to bring the 2, so it's 5 to the power of 2, which is 25. There's no reason to do that. I just thought I'd point it out. And then eventually I go to a calculator if I want an approximate answer. I'm just using my calculator right now. And I get about 2.34. So, looking at example 3, you might be tempted to take the log of both sides here. But I think if you try that, go ahead and pause the video and try it if you want. I think you might find you get stuck. And the reason you're stuck is, like I said, this is actually a trick question. This is not an exponential equation. The x is not in the exponent place, okay? It's in the base. The way that we can do this is we can just take both sides of the equation, I'll just rewrite it here, and we can raise them to the power of, as it turns out, positive 2/3. Okay, so I can raise both sides of the equation to positive 2/3. And when I do my power of a power, negative 3 over 2 times 2 over 3 is just 1. So you get an x equals 1 there. Oh, sorry, this should be negative 2/3 and negative 2/3, my bad. So that you get positive 1, not negative 1. Okay, 6 over 6, or 1, equals 125 to the power of negative 2/3. Okay, to evaluate that, I can just say that's 1 over 125 to the power of positive 2/3, which is the same as the cubed root of 125 squared. Just like that. And it actually does work out very nicely because the cubed root of 125 is just 5, and 5 squared is 25. So we actually get 1 over 25. So I threw that one in there. There's not actually an exponential equation, so just be careful with that. Okay, moving on. Okay, here we have a word problem. Population of a town is 44,000 and growing at a rate of 2.4% per year. When will the population reach 100,000 people? So we've looked at exponential growth problems like this, where we were able to predict populations, but now we're doing the reverse. Now we're given a population and we're going to predict the time. So we might start off with some type of formula. So remember exponential growth, we talked about the general form looking like y equals a times b to the power of x, where a is your initial value and b is your growth rate. In this case, your initial value is 44,400, and a growth rate of 2.4% means we multiply by 1.024, so 2.4% is 0.024. Adding 1 to that gives us the multiplier we can use to the power of, I don't know, we could say n for number of years. So we're able to sub in into this equation and predict populations. You know, if we sub in n equals 10, maybe we get to 100,000. I don't know. But we want to figure out a population when it reaches, pardon me, a population of that. And so we have, again, this is definitely an exponential equation to solve. We're solving for n. So the 44,400 is kind of the main issue. We want to divide that out. That's our first issue to deal with. So that we get some number equals some power, like so. Now, we should probably take a look at like reducing 100,000 over 44,400. So just thinking about that, I can definitely divide out 100. Let's see, 1, 2, 3 over 4, 4, 4. And looks like I can do a little better than that because both of those would definitely divide by 4 to give me 250 over 11. Okay, which is just a nicer number to deal with as opposed to rounding any kind of decimals or anything like that. We can leave it as 250 over 11. And from there, we're ready to take the log of both sides. So the log of 250 divided by 111 equals the log of 1.024 to the power of n. That allows us to bring the exponent down like so. Okay, now we no longer have an exponential equation. Sorry, that's 111. We can divide both sides by the log of 1.024, and that will just give us n. It'll give us that n is the log of 250 divided by 111 all over the log of 1.024. Now, you can reach for your calculator at this point and try to figure out what that is, but I'll point out that there is something kind of neat we can do, and that is we can replace the quotient with the log of 250 minus the log of 111 using one of our laws of logarithms. I just feel like that looks a little bit nicer like that. There's no fractions and fractions or anything like that. And then it's just a matter of using our calculator to figure out what that answer would be. And it's going to be about 34.2. And so our answer is about 34.2 years. Of course, you could sub that value back into the original equation as a way of checking your answer if you wanted to. Okay, one thing we've talked about already in this course is half-life. So in this question, we have 20% of a radioactive material decays in a 40-day period. Find the half-life of the material. So we're given kind of a data point that in 40 days, there's a 20% of a material decays. We need to find the half-life in this case. So if we imagine trying to set up a half-life equation here, we might have some type of equation like the amount remaining, and they've given us percent. So if you want, you could use 100 for your initial value. 100% of the material is the initial amount. The decay rate, since we're given half, right, we can use a half or 0.5. And we would normally take our time and we divide by the half-life, and that's how we'd approach a problem like this. Normally we'd be given the half-life and we'd sub in the half-life for h, and we then have a formula. In this case, we're not given that. Instead, we're given the fact that 20% of it remains after 40 days. So one way to start this is to realize, well, we know that when the time is 40, that there's 20%, 20% is decayed. That actually means that 80% is remaining after 40 days. So when we sub in t equals 40, we'd expect to see 80 remaining. And now the only unknown is in fact the half-life, which is in the exponent place. So this is an exponential equation. We can divide both sides by 100 to get that 0.8 is equal to 0.5 times, or to the power of 40 over h. Now that might have been the original equation that you started with, totally fine, because this equation is as if you used an initial value of 1 and a final value of 0.8. Well, 100% is the number 1 and 80% is the number 0.8, so it works out as well. Take the log of both sides. Just like that. Okay, bring the exponent down. Like so. Okay, and now we're ready to solve. So I want to get h on its own. You could divide both sides by log 0.5. So you get that log 0.8 over log 0.5 is equal to 40 over h. Lots of options here about how to think about this. You could cross multiply if you like. H log 0.8 equals 40 log 0.5. And then divide by log. Remember that these logs are really just numbers. Okay, a lot of people are confused by log 0.5 and log 0.8, but they are just numbers. At any point in time, We could fill them in we could calculate them on our calculator if we wanted to. It's kind of like when you deal with sine and cosine. The sine of something is just a number, same with the cosine. It's the same with logs. Here's my exact value for the half-life. Then go to your calculator and figure out an approximate value. So 0.5, log of 0.5 times 40. And you get, I'm getting about 124, I'll say 124.25 days. There's your half-life. So notice the log of 0.5 and the log of 0.8 are both negative numbers. That should make sense. Because when you do the log of 0.5, it's 10 to the power of what equals 0.5? Well, that has to be a negative number since the answer is less than 10. So just don't be surprised when you see those negative numbers on your calculator for that. Okay, our last example today involves, it's very similar to the half-life example, but we're talking about doubling periods instead. So we have a town with a population of 500 in 1950 and 25,000 in the year 2010. Find the doubling time of the population, or the amount of time it takes the population to double. And this is assuming that there's an exponential rate of growth that doesn't change. So we're assuming it grows by some percentage, and that percentage stays the same through the 60 years, which obviously is not true in real life, but it still gives us something to work with. And also, exponential growth has the property that the doubling time of an exponential growth model will always remain constant. So if it takes 20 years for the population to double, it'll always take 20 years for it to double, regardless of its population size. There are a number of ways to answer this question. You could approach it like the half-life problem and attempt to use sort of a doubling time equation. You could also just look at the growth rate and attempt to answer the question like that. So a growth rate, of course, if you imagine the general formula for exponential growth or decay, B is your growth rate. And this is something we have done in this class before. If you went from 25,000 to 500 and it was exponential growth, that means you multiplied by some amount 60 times to get to from 1950 to 2010. And that is the same. To figure that amount out, you can take the 60th root of 25,000 divided by 500. Now, 25,000 divided by 500 is in fact just 50. So it's the 60th root of 50. To kind of better understand that, think about it this way. If you multiply 500 by 50, you would get 25,000. But instead of thinking about just multiplying by 50, think about my multiplying by some number by itself 60 times to go from 500 to 25,000, which is the same as figuring out the 60th root of 50. So in this case, we've now basically got an equation for this population. We could say that its initial amount, we could start in the year 1950, is 500. Its growth rate is now the 60th root of 50. And n is the number of years since 1950. I'm not going to worry about what the 60th root of 50 is right now. It's going to have a lot of decimals in it. I'm just going to leave it like that as an exact value. We could check to see that this equation is true by subbing in n equals 60, and we'd better get to 25,000, which I can assure you we will. Now, but we asked what the doubling time of the population was. So what we could do to answer that question is basically say, okay, well, how long did it take the population to reach 1,000? If it started at 500, the amount of time it takes to reach, if you start at 500, the amount of time it takes to reach 1,000 is going to be the doubling period. So we solve this equation right here. It's an exponential equation. Divide both sides by 500, and you'll get 2 equals the 60th root of 50 all to the power of n. Now, another way of interpreting this is you could say that you could treat it like, well, maybe it's, this is calculating, like this is the same as an initial population of 1. How long does it take an initial population of 1 to reach a population of 2? Well, that's going to be the same amount of time as it takes 500 people to turn into 1,000 people, according to exponents, or exponential growth. Okay, back to this equation. We'll take the log of both sides, and we'll get log 2 is equal to the log of the 60th root of 50 to the power of n. That in brackets like that. Okay, now here's a little a slick little thing I'll do. The power of 60 is the same. So the 60th root of 50 is really the same as 50 to the power of 1/6. And so this is really the log of 50 to the power of 1/6 times n. Well, n times the 6 is just n over 6. So there's a much nicer equation to work with. Bring the exponent down. And I get this right here. Now we're solving for n. You can multiply through by 6 if you want. 6 log 2 equals n log 5, 50, pardon me. And then divide by 50, and that would let you solve for n. So n is going to be 6 log 2 divided by log 50, and that is going to be our doubling time. That's our exact doubling time. Of course, we can use a calculator to approximate that amount. So the log of 2 times 6, and then divide that by the log of 50. And I can see, let me just check here 1 second. And I realize now I've made a big mistake, and you're probably a bit confused as well. So if you don't mind, rather than me repeat the whole example, hopefully you can figure out what my mistake is here. It's right here. So I dropped a 0. That's going to be 1 over 60. Okay. So when I get here, this needs to be divided by 60. So the 60th root of 50 is 50 to the power of 1 over 60. Okay. So that makes this a 60. And then we're going to multiply by 60, not by 6. Sorry about that. By 60. And that hopefully gives me a better answer, because my answer wasn't making any sense, and probably you were confused as well. And I get about 10.63 years, which makes a lot more sense for an approximate doubling period of this town. And that's our last example. Okay, thank you.